Hello, this video is going to be about Euler's method, the improved Euler's method, Runge-Kutta and the perfect solution, and comparing all four using or changing the step size. And this problem was taken from one of my college textbooks, which is about 50 years ago. And this is the differential equation that we are going to integrate. Now, Euler's method is a very simple method developed by Euler a long time ago. And basically it goes like this. You have a starting position, y, and we have a function of x and y, which is this right here. And we look ahead one step, and then that ends up being the new position. And this is fairly simple. It works, but the problem is that it assumes that the slope of the curve is constant from the starting point or the starting point of an interval. And if you look at this, we're using intervals of delta t or 0.1 seconds. So the answer is not going to be very accurate. A better method is to look at the interval and use an improved Euler's method, and I've heard this called optimized Euler's method, other things like that. And basically what we've done is we calculate this y prime again, which is this, and then we look ahead one step, which is here. So we're looking at one step ahead for the y and the x, and this is the slope at the end of the interval. In other words, at the beginning of delta t, we have this slope, and at the end of delta t, we have this slope. And what we're doing then is we're adding the two together, and we take the average slope. And this is much, much more accurate than just using the Euler's method. So moving on, there's a better method yet. And basically what it requires is averaging more slopes. So this is Runge-Kutta, and it doesn't take much to implement it. We have an initial slope. This is the same thing as this up here. And then we have the slope that is halfway in between using the initial slope. And then we have this another slope, which is halfway in between, which is using the average slope. And then we have the slope at the end of the interval. So we end up with four different slopes. But what we've done is we've weighted the two middle slopes by a factor of 2, and then we've multiplied it by the delta t and divided by 6 to make it so that it all comes out to 1. So this is 1, 2, 2, 1, which is 6 divided by 6, and we get a much better slope. So how much difference does it make? Well, actually, it's significant. And the big question that one would have is Euler's method is simple. You only have to evaluate the differential equation once. The improved Euler's method, you have to evaluate it twice. So you better get better than twice the resolution or accuracy. But another way of looking at it is you should be able to get a better accuracy with the improved Euler's method using a delta t of 0.1, and that should be able to compare with a Euler's method of using 0.05. So then let's move on down here. We have Runge-Kutta, and here you can see we have to do four slope evaluations. So this better be able to solve the problem with much bigger steps than what you would use with the Euler method alone. And this is the perfect solution from the textbook, or actually I think I solved this. And now we can do a comparison. So I just compared a few steps, and you can see that we have Euler's method, and it's not following the perfect solution too well. The perfect solution is this dot pink line. And then you can see the improved Euler's method, even though it required twice as many steps, it's definitely worth it because it follows much closer than um, the normal Euler's method. And then we have Runge-Kutta, which is the green line underneath, and you can see that it is almost perfect. So let's just move up here a little bit and take a look. And here you can see this is the perfect solution here. So after 12 steps, you can see the Runge-Kutta is pretty close. I wouldn't call this close enough for real mathematical use, but you can see that it's much different from the Euler's method, the improved Euler's method, and then this is the perfect solution. So what happens if we make the gap smaller? So we're going to make this gap 0.5. And obviously we're not stepping quite as far here, but you can see that this is still not very good, but the improved Euler's method is closer, and there is hardly any difference at all between the Runge-Kutta and the perfect solution. But let's move this up again and make this a 0.01. And here you can see that the Euler's method still has significant error, whereas the improved Euler's method and Runge-Kutta do not. So the point that I'm trying to make is that even though Runge-Kutta requires 4 times as many calculations, it's definitely worth it because overall, to get the same number or the same level of accuracy, the steps don't need to be as small. So even though you're doing 4 times as many steps, your steps can be maybe 10 times or 20 times bigger than what they can be with the Euler method. So what brought all of this on? Well, I've saw lots of YouTube videos talking about Euler's method and about how it was used in the space program. And I find that hard to believe. I think that Runge-Kutta would have been used. And the reason why is that Runge-Kutta was invented around the 1900s, so it was definitely available or known around the time, the mid-century when they were starting to look at launching rockets. So now, uh, how does this get used? Because this is a very, very simple application. We're only integrating just one function. And whether you're using Euler's method, improved Euler's method, or Runge-Kutta, you can always apply it to many different equations at the same time, which is what I'm going to show you now. And this is a simulation for a hydraulic cylinder. And basically, instead of just having an X and a Y, I've got many, many states here. I've got a state of the spool, position, velocity, pressure in the A volume of the cylinder, the pressure in the B volume on the rod side, the velocity of the actuator, the piston, the position of the piston, the control output, the flow of the pump, and the gas volume within the accumulator, which is trying to keep the pressure constant. And this is all the math required. And you can see that this is, 9 differential equations here. I'm not going to go into all the details because that's not that important. But the big thing is that down here, I can solve for the differential equations and do a very good simulation. This is where I simulate a bump or an obstruction in the cylinder. And you can see I can plot out the supply pressures, the pressures on the A side, pressures on the B side, velocities. Come down here a little bit more. There's where I simulate the force impact on the piston. This is where I'm simulating the gas accumulator volume. So as the system is running, the accumulator tends to run dry or empty. So it has more and more gas in the volume, and less oil. But then what happens is the pump starts coming online, this is the pump up here supplying the pressure. And you can see that the pressure only drops so far, which is what I'm interested in. And again, this is the flows, pump flows, and the pressure and supply pressure. And this is the position and velocity. So I've got target position, actual position here, and the target and actual velocity here. And you can see the control output where it responded to the impact. So you can use Runge-Kutta or any of those differential equations or methods to be able to do the same kind of calculations, but I use Runge-Kutta for a couple reasons, and that is I don't have to do as many iterations. And after a while, when you start doing a lot of iterations, you start to wonder about round-off errors. Now, that's not so important anymore. Um, in today's math, because what happens is you have 15 digits of resolution, and chances are the information that you have or your model is not going to be near that accurate. So Runge-Kutta fixed works just fine. There is a Runge-Kutta with where it's got a variable step where you can step farther ahead, but then the problem is that you don't have information at every even increment, which is what I desire. So uh, I like to use Runge-Kutta for fixed. And another reason why I like it is that if you ever run up against a stop, it's easy to restart Runge-Kutta with a different step to make up for the rest of that time period. So in other words, if you have a step of a tenth of a second, but you end up hitting an obstruction, for instance, your system stops, you might be able to take off after half a step, or instead of a tenth of a second, after a half a second, and you can change the time period and start all over again to get started again when the obstruction clears. So this is just calculations for the PID. So you can see that with Runge-Kutta, you can have many states, and you integrate them all at the same time. So that concludes my video. Hope you enjoyed it. Bye.